Right, hello everyone, and welcome to this IAQM webinar on driver behaviour changes, how telematics can inform the changing new normal in vehicle emissions in the UK. Today we are joined by Dr Sam Chapman, co-founder and Chief Innovation Officer at the Floow, a globally recognised supplier of telematics solutions. Sam, as well as growing the Floow, holds roles representing his region's digital sector, his local Chamber of Commerce, as well as various parliamentary expert groups. He remains personally committed to improving air quality, having run many air pollution research projects. Today, Sam will explore how COVID-19 has impacted driver behaviour and subsequent vehicle emissions in the UK, and will discuss how large-scale telematics can offer insights in this area. As always, there will be the chance for questions at the end of the presentation, so please do submit these in the Q&A option at the bottom of your screen. You can do this at any point during the talk, and I will then ask these on your behalf after the presentation. Thank you all for logging in. Thank you, Sam. I'll now hand over to you.
Hello everyone. So let me jump right into it. I'll give you a quick outline of what I'm going to talk about today, just quickly for those that don't know who I am, who is the Floow, the company I'm from, and follow that with information on new mobility data and how that can help with vehicle emissions. I'll talk about a large research project that's looking at this area for a longitudinal study in this area and early work in that, and how we can use that information to help better understand the changes in particular to emissions. And then finally, the thing that's obviously building the title, COVID and the changes to driving behaviour. So let's move straight on. So who am I? I'm an academic by background, but turned entrepreneur, co-founder of a company with quite a lot of people in now, focus on innovation in a whole range of areas, but most importantly for this talk is I'm a father of a child that has quite severe asthma to the point of ICU admissions and so on, which has led me to quite a personal aim to really push in the area of how we help with pollution. So we are a company of 120 people headquartered in the UK in Sheffield, but we do work all over the world. What we do is telematics. So what that means is we gather information from a whole variety of different devices, whether that be in-car electronics, smartphones, plug-in devices, black boxes you may have heard of. But all of these devices are there for one reason, they're to capture information about a vehicle's movements, how they move through the environment in such a way that it can be analysed and fed back regarding risk primarily. So we're globally recognised in the insurance sector, and there's some names popping up here that are useful to understand in terms of where we get our data from. So in the UK, two of the top three insurers, Direct Line Group and Aviva, give us data for all their track policies in terms of the movements of vehicles around the road network. But we do this all over the world. Munich Re is a global agreement. And there are many other examples in here also looking at wider areas in terms of mobility as a service and other sectors. What we do for our insurance partners is we act as a data refinery. We take information from vehicles as they move and we process it to understand that mobility. So we get fine-grained information of a vehicle moving down a road, its speeds, acceleration, its behaviours, its movements, and we use that in order to predict risk. We look for correlators of that subtle behaviour changes that look to examples of certain behaviours that correlate to risk. So how does this all relate to new mobility data and how can it inform into vehicle emissions? Now, obviously, with that global presence, that's petabytes of data. There's millions of miles of data gathered in the UK daily. So in terms of giving an impression of what's happening on the road network, it obviously gives us fine-grained data, but how does it help inform into vehicle emissions? So first of all, there is let's play. Okay. Regardless of the device where data comes from, it can help build up a picture of normalised behaviour by any location. So what you're seeing appearing on this particular image at the moment is a plot of speeds that are being generated by mass vehicle movements that fill up the entire network that typify the standard behaviours on those road networks. And obviously, you can get very complicated about the type of data that you store, the type of data that you can capture, but you can build up pictures and patterns of behaviour that cover everywhere. And that's obviously more interesting from an air quality point of view, because it can give you data and information that can feed into processes that wouldn't traditionally be gathered only at fixed point monitoring or certain surveys or where there is actually monitoring stations. So it gives you a richer source of potential data. Now we aggregate this data according to a map. So we create a map of the road network and we base this on behaviour. So shorter segments where behaviour changes more frequently and longer segments where it's long and straight and not much differential behaviour occurs. And that includes bidirectional information over the entire road network of the entire globe. And for every vehicle we ever see passing there, we collate that behaviour to build up patterns of what that behaviour of vehicles is at that particular location. So you can use this to get statistical data gathered across very large regions. So this is a quick snapshot of the UK and some passage of vehicles travelling around on it. And you'll see that there's different colours related to different types of behaviours in different centres and so on for different styles of driving in this particular plot. But obviously you can do more with this. Now, one thing that we did, and this is warning, this is old work and one that has a number of glaring simplifications, so it's just an example. So this was in 2016. We used this to calculate Knox emissions for the entire UK. And when I say the simplifications, it was based on a flat map and everyone driving the same vehicle. So in terms of accurate emissions mapping, it was very much rudimentary. What this was designed to do was just purely to identify regions that may not have air quality management that should. So in terms of actually trying to identify the concentrations of where NOx was potentially problematic but not being looked into. Of course, fine-grained studies are needed. And the reason for this is when you look on a large-scale basis and make such generalizations over data, you admit the certain local deviations that occur in data, behavior, understandings of the localized environment that aren't necessarily featured in these large-scale models. This is particularly obvious when you start looking at extreme behaviors, and I've got some examples here. What you can see in the areas of these maps that are colored in red is areas that have extreme behavior. So this is on the kind of 98th percentile of accelerating behavior. Those that really do, on dynamics of a vehicle, produce an awful lot of pollution, and where they occur and the frequency to which they occur. So if you look at London, the frequency of those is actually all on side roads, none of it on the arterial roads, and probably for very good reason. There are cameras, there is congestion, so therefore you will find that behaviour happening on those back street roads. However, if you look in other parts of the country, you'll see very differentiated and localised driving dialects, effectively, of how people drive, that people pick up from the environment around them and drive in a differentiated way. So if you look to Sheffield, all of the instances that are there coloured in red are all around junctions. If you look to Glasgow, all of the instances are actually, and somewhat counterintuitively, on the main arterial roads around the area where there is the only place that's monitoring, and that's where the excessive behaviour is occurring rather than on the side streets. So these localised driving dialects mean that large-scale studies need to take this type of data into account in order to actually be predictive of behaviour by each location. Large-scale studies don't necessarily do this, and obviously they're generalised. Now, of course, you can use information from telematics to pick up and understand behaviour from very precise parts of the network as well. And some examples here in terms of looking at the acceleration ranges only on straight sections of motorway, less than 60 km/h without slip roads or turnings. So just to judge the behaviour and the frequency and the probability of certain styles of manoeuvres, and those aspects can be fed into models to understand the degrees of pollution. Same thing in terms of the volume of traffic. You'll see the volume of traffic plotted on this particular graph here. This is for an area in Norwich, indicating the degrees and changes of traffic over the time of day. And obviously these look very similar, but they differ by location to location because localized changes mean different patterns of behavior. And this final one over here is actually turning frequency by junctions, just an example of a few points on it, but actually looking at the clustering of actually which of these passages turn left, turn right, wait, how long they dwell, all around a junction. That's obviously the concentrated locations where pollution does build up. So understanding these fine-grained behaviours on a junction by junction or road by road basis is essential to really understand the types of emissions that are emitted within them, rather than generalising by road type. So what we do is with the data that we aggregate data and normalize it. We process it to remove a bias. We look at it for data quality because obviously these are based on GPS devices. GPS isn't always accurate. Once you run through all of those processes, you can build up statistical impressions of actual behavior by location. So you can build up patterns of vehicle flow, the distribution of speed, not just an average speed, but the entire distribution in terms of how many vehicles travel very slow or very fast. There could be bimodal distribution, for example, near traffic lights where some people will drive straight through, some people wait, and some people will go very fast to get past the light when it's changing, for example. So we've got wide-ranging behaviors. And the same thing for acceleration. Where you get wide ranges of acceleration, obviously there is more complicated interactions when it comes to the amount of pollution that gets emitted from vehicles. Also looked at is congestion and idling that via wide locations and can be calculated in order to help understand and feed into models, which is particularly important when looking at certain areas, particularly around things like school streets, where you have certain patterns of behavior that isn't necessarily conducive to a clean air environment with large numbers of people waiting around, not really moving, but still in a vehicle and moving slowly in slow congested traffic. So what does this look like when you start looking at the data? You can start to see acceleration levels by locations. So in this particular plot, you can see the coloured in the more orange is obviously where there is higher degrees of acceleration. So you'll see concentrated areas whereby there is a localized spike and where engines on vehicles are more utilised in order to create the motive power for that acceleration. Where that occurs, obviously there's a localized concentration of output and emissions. And you can see that by junction, by road, by segment, very clearly across the entire network. Now, of course, this differs by time of day and conditions and time of year. And here's an example showing, I think actually from the same plot previously, I think the same junction towards the top left, you see that there is by hour of day changes in this. And you'll see the colors changing on this over the day as an aggregated picture of what normalized behavior is over those particular sections. This isn't just a snap survey or a clipboard study. It's actually aggregating data over a long period of time to get to a normalized statistical view of how busy and congested these roads are. And that's obviously useful information, again, to feed into various studies. So in 2016, we started a series of works looking at pollution in particular and using this data in new ways, because previously to this, we've been using it for insurance and risk understanding. So in this particular sense, we partnered initially with James Tate at the University of Leeds, whereby we started to look at the second-by-second movements of vehicles so that we could use this to characterize and understand the behavior and movements through particular sections of the road network. So this was in the Leeds gyratory, an area that's particularly problematic for air quality, and looking at conditions whereby vehicles are traveling under free flow, stop-start, but over a whole periods of different times of the day, different conditions and different criteria to evaluate actually where was the contribution to Knox in particular in this study was coming from. So in terms of the cumulative impact, despite a faster traveling vehicle, therefore emitting reasonable pressure from the rate of the engine, but obviously the stop-start traffic and the build-up over time for that same distance generated considerably more Knox. This is just an example from 2 journeys. Combining all those together, so looking down an individual route, you can start to come up with the exact impression of where that pollution is being generated. So you can start to see at the beginning of the route or where it happens around key junctions or where queues start to form, we start to get more of an impression, but it gives an evidence base that can be replayed and also tested against different Euro classes of vehicles. So for the example here, this was testing against Euro 5 diesel for all the vehicles that were passing there to understand what would the mix look like if it was Euro 5, what would the mix look like if we remove some of that Euro 5. And this was used in consultation around the setup of the initial planning stages for the CAZ that was planned in Leeds, and identified key problems that they had to solve. And the key problems were in the evening rush hour going southbound on this particular stretch of road rather than northbound. So obviously this is dependent on different roads at different times, have very different challenges. But using this evidence can help to identify where's the problem that you really need to solve, where the concentrations become the highest. So that was quite some time ago. I just wanted to tell you a little bit more about a more recent and ongoing project where we've taken those ideas much, much further. And then I was going to get onto COVID specifically and the changes that you see on the network. So Wmai is a research project funded by NERC with a large range of partners, and it's led by the University of Birmingham. Across these partners, there's a whole series of regions, so Transport for the West Midlands, there's also Birmingham, there's also the West Midlands Combined Authority, also, and so on, as well as firms involved in the deployment of transport solutions, as well as monitoring, and also the health impacts as well. So there's quite a wide range of stakeholders, and it looks across a lot of different factors. The key aspect that we're involved in is about the vehicle emission side. So obviously this is a wider project with a large amount of research in a whole series of different areas that impact on air quality. What I was going to talk about mostly is on the vehicle emissions side, however. So on the vehicle emissions side, that's a subsection of the prior partners, and this is headed by Professor Francis Pope, who we work with quite closely in utilising the types of data that we've got in order to understand the pollution across the entire region. When we say entire region, we've limited this to looking at the entire West Midlands Combined Authority with information on every road for the period 2016 to 22. So this is a longitudinal study looking specifically at change, looking specifically at what happens from year to year, how it evolves, how that change occurs, so that you can use it to understand how certain programs and interventions have been successful, which policies are helpful. And this was designed to run alongside the CAS introductions in Coventry, in Birmingham, and so on, which obviously have had some delays because of their recent circumstances. This has given us an opportunity from this basis to start exploring other areas of how we can use this looking at data to actually inform about things like COVID. So this project evaluated a whole series of different characteristics that we were collating information from the road structure itself that can be fed into modelling and solutions to understand air quality. So they relate to the time related, so the time spent driving. This is on each individual segment, so the amount of travel that's over there, how much of that time is cruising, accelerating, braking, standing, just idling, or whatever else. The speed related or acceleration related or stop related, how many stops and starts there are, as well as the full dynamics. So this is the physics of each vehicle passing over that full time period over those roads to be able to feed into physical emission models that can then feed out emission values for each segment of road so that we can use that later on. These also don't just take that information across entire years. We can obviously break that down in lots of different ways. So here's an example from 7 till 9 in 2016, from Tuesdays to Thursdays only. So morning rush hour, basically, on a weekday, on a standard weekday, not the Monday and Friday. And from that, you can start to see, so the maximum speed, here's the maximum speed for the entirety of the West Midlands, taking into account Birmingham, Coventry, and so on, for all the roads around it. And you'll see that off the Birmingham box, which is the motorway box structure that goes around the centre of Birmingham, all the roads off the edge have this higher colour of yellow, even though they're not on the main arterial motorway roads. That actually is high speeding vehicles going off those, but you also see speeding going on all over the place throughout this. But this is gathered right down to every individual residential road over the entire area where there is data to be able to do so. Now, from this, of course, you can get vehicle-specific power. And vehicle-specific power is often used in terms of a whole range of emissions analysis, and they've been calculated on a segment-by-segment basis, going northbound, eastbound, westbound, or whichever direction the road is in both directions. And it takes into account the inclination of the land, the type of vehicle, the rolling resistance, the aerodynamics, in order to actually pinpoint the value. So obviously, you can do different versions of this for different types of vehicles. In order to get different values. What's plotted here is a generalized view of the standard mix and blend of vehicles over that network, because elsewhere in this same Wmai study, There's a evaluation of the fleet mix, also the emissions using EDAR laser-based studies over the road that's looking at actual exhaust in real-world conditions. And using that, you can take this information and put it through using these contributions and mixes, as well as the emission factors, to deploy that information to then come out with exact emissions for all parts of the road network, which feed in information and provide readings such as CO2. So you can start to see for the individual road section per vehicle that passes the normalized grams that are being emitted. And over those aspects, that allows for the potential of routing to avoid where the behaviour or the road infrastructure is structured in such a way that leads to excess pollution. It also allows an understanding when using Floow in combination with that information to be able to scale that up to give out emission values across the entire road network. Now, across the emission values, obviously there is a comparison here being taken with looking at the mean, the median, and so on, as well as the distribution across all the segments within particular regions. And they have to correlate back to real world readings that are obviously undertaken in those networks as well to look for correlations and where these are balanced. So obviously there's a long tail to the right of this normal distribution, whereby there are some small sections that leads disproportionately very high amounts of pollution because of the localized behavior that occurs on those sections, or the nature of the road that's increasing the amount of acceleration and braking very localized to them. Now, this can be done, of course, for a range of different emissions. Here's also Knox as an example, which has a similar degree and pattern of emissions over the region. So these, what we're doing in the project is using these figures to then work in very large scale and provide new capability. So looking at all schools and services across the region to be able to say, actually, from the exact knowledge of the pupil population, their catchment region, the exact location of the school, all the roads in surrounding and within that catchment, we can actually calculate the level of exposure for the students within that school, and depending upon how far they are away. And we can provide that information to help form plans that help change the infrastructure and the road network in such a way to minimize this. Now, that work is obviously ongoing, and so this project runs till 2022. And obviously the original intention was to look around various mitigations like CAZs in terms of the behavior before, during, and after the incorporation of those, alongside the transition of vehicles, whereby newer and cleaner and greener vehicles are adopted, and to see actually what that means in terms of the overall outputs and what approach is working best to drive positive change. However, with the CAZs held in abeyance, with the world somewhat changing because of COVID, there's been a little bit of a focus also towards looking at COVID in this project. Now, we haven't just restricted that to looking in the West Midlands area, we've been looking across the entire country in looking at this. So this slide is kind of obvious for anyone that knows what COVID is. So obviously in March, there was a severe impact, and it started in the stock exchange before it started in the actual the behavior that was observed on the roads. Sorry, my screens are shifting for some reason. Apologies. There we go, back again. So with the behavior change on the roads, that occurred approximately 2 weeks later. What the government showed on this was information that related to showcased the changes from the related to various forms of transport and how they decreased. Now, what's less known about these plots that are obviously put out by central government is they are based on only 285 data points, where they're gathering the data of vehicles passing them as a representative sample for the UK. Now, they've been carefully chosen, so they are actually very representative for 285 points, but it's still only 285 points. Now, we've been using billions of data points in terms of actually looking at the behavior around COVID and the changes of where and how that's impacting. So I was just going to detail that quickly. So if I jump back to the last slide, you'll see where daily journeys in the UK didn't quite have that subtle fall off that was presented by the government. It actually had a sudden crash at a certain point, somewhat after the FTSE drop. And in parallel, up until May, was following quite closely in a kind of combination of the economy matching the change in transport. Obviously, the economic effects of the decreased transport have an impact, but transport has now risen again, and it's changed more. Now we'll get on to more the aspects of how that's changed and why now. So in terms of this analysis, we've looked at the change in travel times. Now, you may well be aware from local studies, obviously, that people are behaving somewhat differently. No one's going out in the evenings, particularly during lockdowns. So there is a change in behaviour. Many more people working at home. There's different differentiated direct deliveries and so on. But the overall changes, even in the period leading up to and even during the announcement, actually didn't change initially. What you will find is at the beginning of this block that's in grey was when it was first announced in the House of Commons that a lockdown would be coming. At the end of this block is when it was enacted. So even at the beginning of when it was announced, actually the standard pattern of normal 9 to 5 AM peak and PM peak tended to hold true. And regardless of fluctuations by day and by a day of week and so on, that pattern was very standardized across the year. Now, this is across the entire country and gives you the impression of how that change occurs. Now, obviously post-lockdown, when that first announcement came in, there was obviously a complete and sudden cut-off and change of behaviour. And you can see this in terms of the times of day of travel. There is no longer these little bits at like 2, 3 in the morning or 1 in the morning of hanging over from the night before, particularly around the weekends of people travelling at certain times. But also the peak periods that just almost disappeared overnight. Now, obviously, things have returned somewhat more towards normal since that period of time and has crept back in. Particularly the AM peak has got a closer, but the PM peak, sorry, the AM peak has still been somewhat differentiated, and it's taken much longer to return. Now, the patterns of behaviour now are still somewhat differentiated. So the normal that is now, despite the fact there is an increase of traffic, is not the normal we had before. And it's still changing. It's still under evolution. So it's not something I can say, this is what it's going to be like from now on, because it's clearly still something that's evolving. If we look a little bit more in detail at some of the information from that we can view across mass numbers of journeys, looking across the entire country, at the duration of journeys, then there's a fairly standard pattern that's been very unchanging from year to year. Even from seasons doesn't change too much. You get more slightly longer journeys over the summer period as people take longer trips. But in general terms, there is a broad pattern of behaviour that tends to hold true. Now, these figures differ slightly from DFT because we have an awful lot more data about short journeys that are undertaken by citizens that is not necessarily always well captured by DFT because they only have a limited, i.e. a handful of monitoring points where that is actually maintained and monitored. So what this represents is the volume of journey numbers according to the distance. And over February, it differs little from January. The grey bar here is January in comparison. So you'll see there's very little difference and it follows the same curve. And that's pretty much standard if you look back the 12 months previously. However, in March, where the news came out, then obviously there starts to be a decline, particularly in the longer journeys where things start to slip. And these slips are very slight, but actually those slight slips are actually quite large in comparison to changes that have happened previously. What happened next, however, was much more severe. So in April, there was a very large change. And obviously this change highlighted around those longer journeys that got cut from people's travel behaviours. So the shorter journeys more so remained. And this obviously represents those shorter travels, the essential trips or key worker journeys to and from localised work settings whereby unable to change patterns of life or shopping behaviour that's leading to aspects of continued journey. There may be many other reasons behind that, but that exemplifies that, evidences that type of behaviour. Now, over time, these patterns have reverted more towards normal. So the journey duration, now, despite the fact that people should still be remaining more in lockdown, there should be less consideration, that there is a more of a return towards normal than previously would have been probably supposed. So from April, obviously, it was very suppressed. May, June, July, by July, it pretty much got back to normal. And over the summer periods, even there was an increase, obviously, in the longer distance journeys from July, August, and into September. And in those periods, those increases obviously match to normal seasonal increases. However, I'll show you later how that may affect regionally. If you look at the frequency in terms of the rate of change by the journey duration, obviously you can start to see the effects on the different degrees of journey length and how they are changing over time. So in February, there's a line very much approximating January. It's slightly differentiated and raised here because a few people are taking longer journeys, because obviously in January you have a little bit of a lull after Christmas of long journeys and travel anyway. So that kind of peak is fairly normal. That's a fairly normal pattern. When you get to March, however, already there's been an impact, a change that started to occur, but less so, very much less so. In fact, 100% exactly the same as normal at the very, very short journeys. The longer the journey, the more the impact, but the very long journeys seem less impacted than those around 50 minutes in length, which has had the biggest impact and cut. April, however, was where the biggest hits were felt, and phenomenal changes to the transport usage of the UK, whereby the vast majority of the travel durations, obviously this is a lower population of the number of journeys in total, but of those journeys that happen to be long, there's only about 20% of what there was before. However, in the shorter journeys, actually some of those are actually maintaining above the 60%. In the very short journeys are actually very little changed, despite the fundamental changes overall. So there's this resistance to moving these last mile and few journeys is obviously still there, and where people are still feeling the need to use motor vehicles in short and particularly very short journeys. This evolved again over time and started to normalise back, and obviously over not in June but in July, August and September, that started to peak over the January figures, which is to be expected in terms of the amount of normal seasonal change in terms of increased higher distance travel that does occur over those times of year. If you look at distance, there's surprisingly less change in the amount of distance that does occur. So in February, compared again to the grey background of January, and that's the area behind, so this is almost an exact line in terms of February, the distance in terms of from those journeys that are short towards long, absolutely the same distribution. There's very little change from February to January. Even when you look at the curves, they lie exactly on top of each other in terms of those distributions. Even looking at a log frequency, you can see very little difference between them. Obviously, things change a little bit more when you start to go to different periods, but even then, these are subtle drifts in terms of the overall movement of this curve, slightly downwards in this direction, over towards the a decrease in distance and decrease in frequency, but almost universally across all lengths. It isn't just applying to long journeys, it's applying to all journeys almost uniformly at this point. There's obviously some uncertainty in this area. It does wobble around quite a lot. April, however, where the larger collapses occurred, then you do get more of an impact in terms of the decrease of journeys from the those that are 40 kilometers or 40 kilometers long or longer, which are actually less than 20% of prior journeys. However, even in this peak period whereby traffic was deemed to go at 20% of what it was in terms of passenger car journeys, there were still passenger cars at 40 to 45% of those short journeys still being undertaken. And you can see here, obviously, the effect of the curve. You can see how this changes again over time, and you can see how that evolves and starts to then approach more normality. Now, what this means is that the new normal that's occurred, although differentiated, is converging to a sort of behaviour that's very different still, but the length and distribution and types of journeys that are undertaken are still not too dissimilar to what was happening before. Now, obviously, that has a huge impact when you look in different ways. If you look geographically towards retail centres, for example, without parking in big covered areas, obviously there is very little traffic going to and from them. That's where before it would have been huge. If you start to look at this regionally and start to look for localized behavior change, you can start to see more differences. So dividing the country up into a series of grids, you can start to look at each individual area and the differentiated impact over time by day of year in terms of the changing travel patterns that have occurred in them. So in this particular example, there is a slight grayer line under here, which is the national average. And the blue level is that of the individual areas. So there's Southport, which is pretty much matching the national average, apart from a couple of days over here, is very, very aligned to the national average in comparison. Sheffield, however, has a decreased amount of traffic over the national average. So for the level of traffic that it had before, it's actually had a larger effect, a larger decrease in its traffic than it has in other regions. Over the national changes that have occurred. Now, obviously, you may have seen news reports about people flocking to Devon over the summer, and here's clearly a demonstrator of that, whereby a lot of those longer journeys you saw before are likely travelling to and from the south of England or the areas, and particularly around the weekends. And you can see that effect over here with the blue, which is obviously spiking on each of these blue bands being the weekends. So you'll see the spike here, spike here, spike here on every weekend. And the ones that spike less is dependent on the weather. So you can start to see the patterns of behavior actually increasing over the norm. In fact, over the norm for that period, way over nearly towards 200% of where traffic was within that region. So there are regional effects. Now, obviously, looking more fine-grained, you can get a very precise view of the types of traffic and how that's impacting and feeding into pollution. But ultimately, what we wanted to make clear in this talk was that the changes are regional, they are differentiated, and they do change quite dynamically by location depending upon localized behaviors, which are different. If you compare one city to another, that doesn't mean they are the same. The main conclusions I wanted to try and draw from this is that to understand pollutions, particularly in periods of societal change, it is not wise to trust prior models based on legacy data. So prior transport models are particularly untrustworthy at this point. Obviously, many of those have had some updates or some recalibration to try and represent data as they go, but they've not been configured for that. They're not getting a true accurate impression, and even worse so when it comes to air quality. National generalizations will never truly represent localized behavior and nuance, and you do need to look at the local data within an area to get a true understanding, which I'm sure many air quality professionals in the room will understand. But what you can do now is you can fill a lot of those evidence gaps, and you can get full coverage, which has been largely impossible before in terms of seeing the behavior on every road. So new mobility data can help this, and this is the focus of the talk, to try and identify where this can actually help support. And obviously this is something that we've been doing within this project, but also wider in other areas. Well, what I wanted to do now is to move towards questions. I think I've done a lot of slides. I think I'm about the right time. So I think it's about question time.
Thank you, Sam. That was really interesting. Amazing to see how you can get both such broad and granular data, and those differences in driver behaviour in different regions was really interesting. So as you said, I'm going to dive straight into participant questions. So anyone that has a question, please do pop it in that Q&A function at the bottom. So to kick off, there's some general questions here about telematics data. Do you have an estimate on the proportion of journeys made which are covered by the telematics data? And how representative is the data in terms of driver behaviour and vehicle types?
So in the UK, this is in general, not just our data, but across all telematics data that's covered in the UK, it's approaching about 10% of vehicles are tracked. Obviously, the way that we gather data, gather it over an extended period of time and use it statistically to understand what's going on, in the same way that you would place a particular manual survey at a particular point for a period of time and long enough to gather enough impression. However, we can go back over several years or look in specific months and different times and midnight in areas of the network you can never examine otherwise. In terms of representation, as it's based on insurance data, it has wide and distributed geographic coverage. Insurers are very keen to make sure they don't end up with a bias of lots of policyholders in one area, because if that area gets struck by some natural disaster, the impact from them on reinsurance is huge. So they do put a very wide demographic and a very wide spread across the country. Now, there is a higher number of drivers that are younger, but they do stretch all the way up to 50, 60, but very few old drivers are included in this mix. However, what you do get is representative behaviour travelling down roads, and within urban settings, when vehicles follow each other, they are broadly representative and being correlated back to other studies to prove their validity. So in terms of reusing this data when it's used in fine grain, it is representative enough to prove the behaviour by location, and that's been tried and tested over many times.
Great, thank you. That makes a lot of sense. And another question to do with, so you mentioned obviously that you can get this data about emissions and exposures on a very local basis, and that this could inform plans for trying to reduce emissions in certain areas. Do you have any examples of how this is being done or how it's being planned to be done? So what can be done to actually use this data practically to improve air quality?
So at the moment, you can use this data in a whole variety of different ways. Obviously, for any intervention that's been put in the past, you can look at prior to that intervention and afterwards, because obviously this data doesn't mean you need to go there and physically monitor. You can just look back historically, it's all stored. So there's an ability to look back over a long period of time to work out actually what are effective measures, what actually delivers a change, is the first potential. In terms of using that data on a day-to-day basis, in terms of looking at it, it is about strategic plans. It's about building up a statistically valid pot of data to be able to be used within a study. Now, we do an awful lot of work in this area around low traffic neighbourhoods, and we supply a lot of data behind a large number of them across the country, that's indicating the amount of rat running behaviour through streets, for example. But in terms of the impacts then that has upon emissions is the next step of how we look at this in terms of what those impacts are. In terms of the impacts at the moment, that's largely being investigated in the West Midlands study area, where we're looking from year to year in the study, so it's 2016, 18, 20, and so on. And we're looking in big chunky periods to look at societal change over those periods, and then where and what those changes are and how we account for them. So we can then work out what is an effective measure and what is not. Now, this project is obviously ongoing, and the final results of it will not be out till 2022. So there's still some time before we'll get to clear understandings of those. Now, regarding COVID, of course, we've obviously looked at the changes of behaviour, and obviously there are changes of behaviour linked to increases in speed, which is obviously not particularly helpful from an emissions point of view, but offset with the fact that that speed is occurring in areas whereby the road networks are being less congested. Actually, there's less vehicles, there's less impact. Actually, the overall effect is generally positive in the areas where that occurs. But I would say at the moment there is a range of smaller studies in this area rather than a nationwide study. It's pilot studies and investigations at this point. However, the potential of using this is large across a lot of particular areas.
Great, that's really interesting. Thank you. And this will probably be the final question in terms of timing, but have you collected any data looking at implementation of the London ULEZ and impact on driver behaviours? And have there been any major observations in these areas?
We have not about the ULEZ, but we do gather information across a large number of London boroughs, where it concerns the changes for cycleways, low traffic neighbourhood plans, and so on, where all of that data is available for potential reuse in terms of looking at emissions, and that covers large portions of London. But there's not been a specific study looking at that at this point yet.
Okay, great. Well, thank you so much, Sam, for such an interesting study. That's it from us today, attendees. Thank you for logging in, and I hope you found that really beneficial and informative. Don't forget to record your attendance at this webinar in the IES CPD tool, and you can do this by logging into the members area. As usual, this webinar has been recorded and it will be made available on the IAQM website and on the IES YouTube channel. Please do watch this on YouTube and subscribe so that you know when new videos are added. The next webinar will be an IES webinar on the 13th of January on exploring world-class landscape restoration. Again, this is free to attend, so please do visit the IES website to register. The IAQM webinar series was started this year in response to the pandemic to ensure that all IAQM members still had access to valuable CPD opportunities. We will be continuing this in the new year, so do please keep an eye on the IAQM website for details of when new ones are announced. Thanks once again to Sam for his really interesting presentation, and thank you all for watching. I hope you have a lovely rest of the day. Thank you.